So the next thing we want to talk about is reversible and irreversible processes. So a reversible process is a process where both the system and the surroundings can be returned to their initial states. Now, the term reversible process is quite descriptive. It means we want to reverse or undo the process that just happened. So we're talking here about a thermodynamic process, and we've looked at a variety of these. So the process happens. Now we want to undo that process, or at least we want to think about whether we can undo that process. Now, a key thing here is to realize that to have a reversible process, both the system and the surroundings have to get back to their initial states. And this is the kicker. We need to remember the surroundings also need to get back to their original state to have a reversible process. So we're going to talk about this for a little while. It's very important to realize that all real processes are irreversible. And we'll return to this statement a little bit later on and talk about why this is true. So the particular process that we want to investigate first is an unrestrained expansion. So here we have a vessel that is divided in half. Top half we have a vacuum. In the bottom half we have an ideal gas. And this is originally at state 1. So there's a certain pressure and temperature here. And the whole thing is insulated. So no heat transfer with the surroundings. So this gas undergoes what is called an unrestrained expansion from state 1 to state 2. And the way we achieve that unrestrained expansion here is that this divider or diaphragm is just suddenly removed, just disappears. Perhaps it just ruptures or it gets yanked out or something, but it's just suddenly gone. So instantaneously this ideal gas finds that it can expand into this whole container, and it does so, and eventually it settles out to a new equilibrium state at 2. So this is called an unrestrained expansion because as this gas expands, it's not pushing on a moving boundary. It's just suddenly free to expand into the entire container. So the question we want to ask ourselves is this process reversible? Is this a reversible process or not? And that's what we're going to discuss here for the next while. Well, before we get into that discussion and the connection with the second law of thermodynamics, let's see what the first law of thermodynamics says about the situation. So we're going to treat this entire container as our closed system. There's no mass flow across the boundary. So we have our closed system version of conservation of energy. The heat transfer, Q, is 0 because this is an insulated container. The work transfer, however, is also 0 because notice if we look at the boundary around this thing, there's no transfer of work across that boundary. There's no moving or rotating shaft or any mechanical connection between what is inside and what is outside. So work transfer is also 0. Well, if heat transfer and work transfer are both 0, then delta U has to be 0 by the first law. And because this is an ideal gas, U is only a function of temperature. So if delta U is 0, then delta T is 0 as well. So the temperature at 1 and the temperature at 2 have to be equal because there's no energy transfer with the surroundings during this process. Now, we're going to take a look at essentially exactly the same situation or the same process as far as the gas is concerned, but we're just going to change the configuration here a little. Instead of having a container with a divider in it, I'm going to replace that divider with a piston. So as far as this gas is concerned, it's at exactly the same state as the original configuration. And what we're going to do is very, very suddenly, instantaneously essentially, move that piston to a new location. So we're going to double the volume of this gas instantaneously by moving the piston from there to there very, very suddenly. So this gas is also undergoing an unrestrained expansion. And as far as this gas is concerned, it has no way to tell the difference between this scenario and the previous scenario. It just suddenly finds that it's able to occupy a larger volume, and so the random motion of the molecules makes it do that. So these two scenarios that we looked at are exactly the same as far as the gas is concerned. I've just replaced that divider by a piston because we want to go further and investigate whether we can undo this process or not. And I'm going to need that piston there in order to attempt to do that. So far, from the point of view of the gas, we've made no change here whatsoever. Still, of course, heat transfer is 0, and the work transfer is 0, and delta T is 0. So exactly the same. Now, I want to just touch on this a little bit because this might be a little bit hard to understand. Realize we now have a piston that is moving from that location to that location. So it's a little bit harder to see in this scenario that the work transfer is indeed 0. So I want to address that. Realize here we're talking about the work done by this gas. And we're asking ourselves, as it goes from there to there, is this gas doing work on its surroundings? Well, we've concluded here that it isn't, that the work is 0, but I want to talk about that a little bit more. Remember when we were doing work calculations for closed systems, and that's exactly what this is, we were calculating work as the integral of P dV. And we calculated work in lots of scenarios like this by applying work as integral of P dV. So why is that not true here? Why are we saying the work is 0 when clearly this gas has seen an increase in volume? So the volume of the gas has increased. So why has it not done work on its surroundings in this particular case? Well, the key difference between every time that we applied this equation earlier in the course and this scenario is this word right here. This is an unrestrained expansion. This piston has moved from this position to this position very, very quickly or instantaneously. Now, what is the consequence of that very quick motion? The consequence is that while the piston was moving from here to here, the gas was not pushing on this piston face because the gas consists of a bunch of molecules roaming around moving at a few hundred meters per second. But if we move this piston much, much faster than that, while it's moving, the gas is not pushing on the face. So this gas is not exerting a force on the piston while it's moving. Now, the analogy that I've talked about a couple of times for work transfer is pushing on a wall. And I talked about you could push on a wall all day long, and if there's no displacement, there's no work. Okay? So that's the same as a constant volume process where there's no work transfer. Well, the scenario here is, let's say that you're standing behind a truck and you're pushing on the back of that truck and the truck is parked. Well, that's sort of this initial state. The gas is pushing on the back of the truck and the truck's not moving. Now the truck starts to drive away, and it drives away at 5 meters per second. And you're following the truck, but it's going too fast and you can't push on it. Well, you are not doing work on the back of that truck. Even though you're moving, you're expanding to fill the space that that truck used to be in. If you are not exerting a force on the back of that truck, then you're not doing work on that truck because there is no force. So there's now a displacement, good, but the force is 0 during that displacement, so there's no work. And that's sort of what's happening here. These molecules, this gas, cannot push on that piston face while it's moving, so they don't do work on the piston. That's what's meant by an unrestrained expansion. The piston face is not restraining the gas as it expands. Now, the last thing I want to say about that before we move away from this equation, work equals integral P dV, is remember that every time we use this equation, we wrote down an assumption. And that assumption was quasi-equilibrium, or a quasi-equilibrium process. And that meant that this gas was very, very close to equilibrium during the entire process. And the reason that had to be true is so that the gas was pushing on this piston face while the expansion happened. So a quasi-equilibrium process is when this is valid. An unrestrained expansion is definitely not a quasi-equilibrium process. That's why the work is zero in this scenario, even though there's a volume change. So that was just a little revisiting of this equation, work equals integral PdV, and talking about why it's not applicable in this case, and so the work is zero. So let's return back to this idea of a reversible process and trying to answer the question whether or not this process we're looking at here is reversible or not. Well, now that we have this little piston device here, we can do some things to try to reverse this process. So far this little schematic is just repeating what was on the previous slide. It's just shrunk a little bit, not take up so much room. So now we're going to try to reverse the process. So we show a PV diagram. This is our initial state. This is our final state, state 2. Now remember we concluded that these two are at the same temperature. So point 1 here and point 2 here are on the same line of constant temperature. Now notice I've joined 1 and 2 with a dotted line instead of a solid line. And this is a convention in thermodynamics. When we have a process that goes from 1 to 2, but it's not a quasi-equilibrium process, we typically show that as a dotted line, because we don't want to imply that the intermediate states along here all follow this line perfectly. The gas between this point and this point is not at equilibrium, so we can't characterize the pressure and the temperature and the specific volume of this gas by a single number. So we get from here to here, yes, those are our endpoints, yes, they're at the same temperature, yes, but the intermediate states we really can't say anything about, at least on a simple PV diagram. So that's our original process from 1 to 2. We're investigating whether we can reverse that. So we're going to try to reverse it. Well, in order to reverse this, we need to get the system and its surroundings back to their original state. So the first thing that we're going to try to reverse is we're going to get the volume of this system back to this. Because to reverse the process, we need to get the volume. In fact, we need to get all of the properties of that system back to their original state. So eventually we need to get back to point 1. So we're going to take this gas and compress it. We're going to reduce its volume to get back to point 1. So at point 3, the volume has returned back here. So we're part way along the process of reversing this process. We've been successful in getting the volume back to where it started. So that's an initial step at least. However, if we think about what happens to this gas as we recompress or as we get back to our original volume, we're going to have to move the piston from here to here. Now, this is where the second law that we talked about at the very beginning comes in. Remember we said there's a natural direction that certain processes occur. Well, there is a fundamental difference between the piston moving in this direction and a piston moving in this direction that is very important in this scenario. It is possible to move the piston from here to here fast enough that this gas does not push on the piston face. We talked about that lots in the previous slide. However, it is not possible to move the piston from here to here without the gas being in contact with the piston face, right? You cannot move this piston from that position to that position and not have the gas pushing on the piston face. So you can go from here to here with zero work transfer like we did, but you cannot go from here to here with zero work transfer. So there's a huge difference between this process from 1 to 2 and from 2 to 3 in terms of the work transfer. So in order to get this recompression to happen, we have to do work on this gas. And our sign convention that we've been using all along would call that negative work because we're doing work on our system. But the important thing is the surroundings need to deliver some work to this gas in order to get the volume back to where it started. Now when we do that, when we do work on this gas, notice this is still insulated. The piston face and the cylinder are all insulated, so there's no heat transfer. Well, if we do work on a gas with no heat transfer, then we're recompressing it adiabatically. That's no heat transfer part. And so the pressure and the temperature are going to increase. So P3 and T3 are too high, meaning that they're not back to the original conditions. The pressure at 3 is higher than the pressure at 1, and the temperature at 3 is higher than the temperature at 1. Notice if we did a first law analysis from 2 to 3, Q is 0, work is negative, so temperature at 3 will be bigger than the temperature at 2. And that's what we've illustrated here. So this is our adiabatic recompression. So temperature increasing, temperature increasing, temperature increasing, and we get back to 3 here. So 3 and 1 have the same volume, but the pressure and temperature are too high. So we've tried to reverse this process, and we're just not quite there yet. We don't have to be done. We don't need to get back to point 1 with a single process like this. We can continue and do something else to try get back to point 1, and that's what we're going to do. So notice we've got the volume correct, so we don't want to be moving the piston anymore. So what we're going to do is remove some heat. So we're going to peel off a bit of this insulation, let some heat transfer, cool this off, and come back down to here. So we're going to remove heat at constant volume to get back to 1. And so that's what we see here. Notice insulation is gone now. Q is negative because heat is being removed from the system. And according to our sign convention, that's negative Q. And so on a PV diagram, that would drop us straight back down to 1. So from the point of view of the system only, remember the system is the gas in here, so if we were to only focus on the system, we would conclude we have reversed this process. However, in order for it to be a reversible process, both the system and the surroundings need to be back to their original state. So the problem here is that the system has returned to its initial state. We've been successful in doing that by having these two processes occur, but in the surroundings, work has been converted into heat. So the surroundings needed to supply some work to this system during this step here from 2 to 3. So we used work from the surroundings, and as we went from 3 back to 1, the system returned to the surroundings some heat. So the net effect that has occurred on the surroundings is work being converted to heat. So there has been an effect on the surroundings. So therefore we conclude that our original process, that sudden expansion, was irreversible. Notice sudden expansion and unrestrained expansion mean the same thing. So this is an irreversible process. So a sudden expansion like this, we want to get used to that as being an irreversible process. There's no way we can get that back to its original state without delivering some work to that system, which is going to be returned to us in the surroundings as heat. So work gets converted to heat. Now we want to revisit our original process and do things a little bit differently. So we're going to ask ourselves, what would have happened here if the original process, that expansion, had taken place slowly? So notice that's now going to be a quasi-equilibrium process. So we're starting off at 1 again. We're expanding the gas slowly now. So because we're expanding slowly, work is done by the gas on the piston, and therefore positive work exchange with the surroundings. So work is delivered to the surroundings as we go from 1 to 2. And I've called this 2' because it'll be a different state than 2 in the original process. So this work that's done on the surroundings can store this work somehow. Maybe it's lifting a weight up, maybe it's winding up a spring, maybe it's charging a battery, something like that. The surroundings can store this work somehow. So if we look at this on a PV diagram, the process from 1 to 2 prime now, the temperature is going to reduce. So that dotted line again is a line of constant temperature going through point 1. So our process from 1 to 2 prime, the temperature will reduce. Notice this is still insulated the same as before. So if this gas is doing work on its surroundings, it needs to give up some energy to do that. So its temperature is going to go down. So 2 prime is down here somewhere. Now we say, well, what does the first law say about this? Well, Q is 0 as before. The work is positive. So T2 prime is less than T1. So that's what I've shown here and what I was just discussing. Now we're going to reverse this process. So we have to get our volume back to where it started. So we compress the process back to the original volume. So the volume here is the same as the volume there. And what will happen on the PV diagram is we're doing an adiabatic compression. Notice no heat transfer during this stage either. And so we're going to follow back along exactly the same line. The temperature is going to increase back up to its original value, and the pressure increase back up to its original value. And notice that there's no net change in the surroundings either. So the system has got back to its original state, and in the surroundings there was some work delivered here, and then exactly that same amount of work was used to recompress the system back to its original state. Because notice the area underneath this line as we go from 1 to 2 and from 2 to 1 is the same. It has the opposite sign, but the magnitude is the same. So both the system and the surroundings have returned back to their original state. So we use the work stored in the surroundings to return to 1. So that's the process I was talking about here. So the system and the surroundings have returned to their original condition. Therefore, this process was reversible. So here we've looked in detail at an unrestrained expansion or a sudden expansion, but we want to think about what are some of the other things that make processes irreversible. So the first one in our list here is our unrestrained expansion that we've looked at. Second one is friction. Friction is also something that makes real processes irreversible. And of course, many of the processes that we're going to look at contain friction. And if we think about it, friction would also be an important component of this little illustration that we've been working on. If we go back to this illustration where we had a reversible process because we let this original expansion take place slowly, so that work was able to be stored in the surroundings so we could use it to return back to our original state, and we concluded this was a reversible process. Well, that would only be achievable if this piston could move in that cylinder in a frictionless manner. Imagine this. Let's say that during this expansion, this gas does 100 kilojoules of work on its surroundings. So there'd be a maximum of 100 kilojoules of work that could be delivered to the surroundings. Well, if, let's say, 5 kilojoules of that was consumed by friction, so the air does 100 kilojoules of work, but 5 of it is dissipated as heat as this piston slides up in the cylinder, then only 95 would be stored out here in the surroundings. And when we come to do the recompression, we only have 95 kilojoules of work available. And of course, there's going to be friction during that compression process as well. So we would not be able to fully recompress back to our original state because we lost some of the work that the gas did to heat. So friction is another thing that can contribute to making real processes irreversible. Another irreversible process is an inelastic deformation. So let's say we were to take 2 balls. One is a ping pong ball, and the second one is a ball of the same size, but it's made out of putty. And we were to take those 2 balls and drop them from the same elevation onto a hard surface. Well, if it was a perfectly elastic collision, and the ping pong ball would be quite close to that, it would drop down. Its potential energy would be converted into kinetic energy. They would hit the surface, and the ping pong ball would elastically deform and then rebound back to its original state, and in doing so it would propel itself back up. And we've dropped ping pong balls lots of times, so we know that's what would happen. If it was a perfectly elastic collision and no energy was lost to air resistance, that ping pong ball would return back up to its original elevation. So that, in the limit, if there was no air resistance, that is a reversible process, because that's an elastic deformation that the ping pong ball is experiencing when it's hitting the hard surface. Well, the ball of putty that we drop from the same elevation is going to undergo an inelastic or a plastic deformation when it hits the surface. And of course, it's going to hit the surface and just go splat. It's not going to rebound at all. So all of the kinetic energy that it had when it hit the surface is dissipated into heat by that plastic deformation process, and it's not available to be returned back into the potential energy of the ball of putty being raised back up to its original elevation. So that's another classic example of the difference between a reversible process and an irreversible process, dropping those two different types of balls, one elastic and one inelastic. Now that also illustrates that all real processes have some irreversibilities, because the ping pong ball does not rebound all the way up to its original height. There is some energy lost to heat through air resistance, or a tiny bit perhaps in the material of the ping pong ball deforming. It wouldn't be 100% elastic. There'd be some losses in there as well. The next one is heat transfer through a non-zero temperature difference. We talked about heat transfer at the very beginning of this section between our two bricks. We're going to return to this idea of heat transfer through a non-zero temperature difference and look at it a little bit more detail in the next slide, because it's an important process in thermodynamics. Another one is a spontaneous chemical reaction. So combustion is an example of this, or oxidation. There's a direction that those processes occur that is the natural direction. So if you have a mixture of oxygen and methane and there's a spark or source of ignition of some kind, then that spontaneously converts into products of combustion, CO2, H2O. You can have a container of CO2 and H2O and a spark, and the process of combustion does not spontaneously reverse. Okay, so there's a natural direction that occurs that makes certain processes impossible. Another one is current through a resistance, and this is really just the electrical version of friction, essentially. Electric current flowing through a resistance creates heat. That is work being converted into heat. If you take a resistor and warm it up, current doesn't just start to flow. Okay, there's a natural direction that's going to happen. So next, I want to expand on this number 4 here, heat transfer through a non-zero temperature difference, because this is a really important source of irreversibilities in the types of systems that we're going to be looking at in this course. We're going to look at heat transfer through a non-zero temperature difference by using this idea of thermal reservoirs again. So we have a high temperature reservoir and a cold temperature reservoir sitting waiting for us. And so the process that we want to investigate is heat transfer from the high temperature reservoir to the cold temperature reservoir. So similar to our sudden expansion, we're going to begin by just letting that happen. So we're going to connect our high temperature reservoir with our cold temperature reservoir and allow 1 joule of heat to transfer. So the high temperature reservoir and the cold temperature reservoir, we're just putting, let's say, a copper rod between the two of them, and just heat is conducting through that rod from the high temperature to the cold temperature, 1 joule. So that's our process. Now we want to see, can we reverse the process? Well, we know already from our initial discussion that the only way to get heat to transfer from cold to hot is by doing work on it. So we can put a refrigeration cycle in here essentially. We can pull that 1 joule of heat transfer that we originally transferred here. In other words, we can try to undo that process, but we have to provide work in order to make that happen. So if we have 1 joule of heat transfer coming into our cycle here, and W joules of work being done on that cycle, then there must be 1 plus W joules of heat being transferred into the high temperature reservoir. So because of the Clausius statement of the second law, it is impossible to reverse this process. Here's our original process, 1 joule of heat transfer. We have certainly reversed that process. We've taken that joule and moved it back up into here, but there has been a net effect on our surroundings, and the net effect is that work has been converted into heat. It comes into our cycle here as work, and it leaves our cycle as heat. So the only way to reverse this process is to convert work to heat in the surroundings. So that is not a reversible process. So work converted to heat, so not reversible.